Okay, what we're going to move on to now is the topic of a very important idea called a vector space. We're going to meet vector spaces when we look at transformations in two-dimensional and three-dimensional graphics. So what's a vector space? This notion is something that allows us to collect together sets of vectors from a subset. All of these vectors have similar characteristics. So what do I mean by that? Well, before going on to that, one thing I should point out is vectors, as we saw in the last lecture, are characterized by an underlying set of numbers, some set of numbers H. And that choice of set is extremely important when it comes to defining what we mean by a vector space. In particular, it has to satisfy this algebraic property of being a structure which is technically called a field. I'm not going to go into the formal definition of what is meant by field. I'm just going to observe that these properties are satisfied by the real numbers and by the integers modulo some constant value arithmetic. And as I said at the start, the behavior of vector spaces is extremely important. It's fundamental to many basic operations supporting graphics in 2 and 3 dimensions. So let's look at some of the basic properties, what we mean by a vector space. What we have is some set of vectors U. These are a set of n vectors formed from some underlying set of numbers H. For example, this could be the set of all 2 vectors formed from the real numbers, and such a set defines a vector space if it has 2 what are called closure properties. First of these is if we add any of the 2 vectors in U, then the result is another vector in U. If we multiply any vector in U by some constant in the underlying set of numbers, once again, that produces a vector in U. So formally, if we're given a set of n vectors from this underlying set H, that set defines a vector space if no matter which pair of vectors we choose in U, so in other words, for every V in U, for every W in U, when we add V and W, we get another vector in U. So this is the first closure property. Secondly, if we take any vector in U, any constant in our underlying set of numbers, we multiply the vector V by the constant we've chosen, then once again we get a vector in U. That's our second closure property. Let me stress again, the underlying set H that we choose our constant alpha from which we form our set of vectors, this is extremely important. So here are some examples. Suppose we take sets of numbers, set of pairs of numbers, which we'll call even, and these are sets of pairs that when we add the 2 elements, the outcome is some even integer value. Now that set, that is a vector space if its underlying components are formed from integers with arithmetic carried out modulo k. So the set 0, 1, 2 up to k minus 1. If we choose our underlying set to be the real numbers, however, then this collection is not a vector space. An easiest way to see that is to look at the second closure property that has to be satisfied. Well, the pair 1, 1 is in this set. 1 plus 1 is 2, which is an even integer. However, the constant a half is in the set of reals, and when we multiply this 2 vector by the value a half, then the outcome is a vector which, when we sum the components, is not an even integer. Suppose we take this definition of a set of vectors, the set of 2 vectors, which when we add the components, we get an odd integer as a result. Then that is not a vector space even for the case we had previously, integers modulo some value, say 16, because if we look at that in detail, well, the vector 1, 4 is in this set odd, 1 plus 4 is 5. Similarly, the vector 4, 1 is in that set, 4 plus 1 is 5. But their addition is a vector 5, 5, and that is not in this set here. 5 plus 5 is 10, which is an even integer. So what are the kind of attributes, what are the kind of properties we have for a vector space? Well, we're looking at a vector space of n vectors, say from the real numbers. There are 2 very important notions, one of which is what is called the basis set, and the other of which is called the dimension of a vector space. So this notion of basis, this allows us to simplify the description of the set of vectors. It allows us to reduce the set of vectors, even if it's an infinite set, to at most some number of distinct vectors. So how do we do this? Well, the key tool we use in doing that is a notion that is called a linear combination. So a linear combination, well, to start off with, let's take some set of, say, m vectors from our underlying set of vectors, from our vector space. So let's denote these m vectors using t sub 1 through to t sub m. We also take a collection of values, at least one of which is non-zero, from our underlying set H. So A here is an M vector. It's a collection, not a set of values. Let's denote that collection alpha 1 through to alpha m. Now what we mean by a vector being a linear combination using the vectors in B, well, all that means is we can form the vector W just by summing over all of the vectors in B the result of multiplying each vector in that set by the corresponding constant value in alpha. So we have these notions of linear dependence and linear independence. What does that mean? So we start off with, we have some vector space U, and we've got some subset of vectors from that vector space. And suppose that has the property that we can take any vector at all, W in U, and we can describe that vector as a linear combination of the vectors in B. In other words, for any vector we choose, any vector W in U, there is some way of choosing constant values with the property that we obtain W as a result of summing over all of the vectors in B and multiplying the relevant vector by some constant. Then, in principle, we can describe every vector in U just in terms of describing those vectors in B. We can construct any vector in U just by using this property that B has, that we can form a vector in U as a linear combination of those vectors in B. So a subset which has that property, a subset B of our set of vectors U, which has the property that any vector in the vector space U can be formed as a linear combination of vectors in B. Well, that set B is what we call a basis of the vector space U. The number of vectors which is in the smallest basis of U, that is what we call the dimension of U. And we use this notation dim U to describe the dimension of a vector space. Now, I hope it's clear that if we take any basis at all of a vector space, any superset of that set of vectors is also a basis. So this notion of smallest basis, this notion of dimension, that is quite well defined. The smallest number of vectors, any basis of the vector space. One property we can see immediately is that any vector space of n vectors, this has dimension at most n. So here are some more examples of this. Suppose we return to this object even that we considered earlier, the set of two vectors, which when we add their components, this gives an even integer. We saw that that was a vector space, for instance, with the collection of integers and arithmetic modulo 4. So this is a finite set of vectors. It contains these 8 vectors here. And this vector space, this is dimension 2. So one basis for that vector space are the vectors 0, 2, 3, 1. So for example, if we look at this element, the vector 1, 1, that can be formed as a result of taking the vector 0, 2, multiplying it by the scalar 1, and adding to the outcome the result of multiplying the vector 3, 1 by this constant 3. Another example, if we take the set of all 4 vectors over the real numbers, then the dimension of that vector space is 4. And the basis for it are these set of what I referred to as the basis vectors in the last lecture, these vectors E1 through to E4. Now it might seem that the dimension of a collection of n vectors, that's usually going to be n. But it can turn out that the dimension of a vector space, this can be smaller than the number of components in the vector. So here's a rather trivial example. Suppose we take the vector space from subset of the collection of 4 vectors, and these are the vectors in which all of the components are equal or identical. Then this has dimension 1 because we can choose as a basis, for example, the vector all of whose components are just a constant real value 1. So just to summarize, this notion of vector space is extremely important in computer science examples, particularly in special cases such as the real numbers in 2 and 3 dimensions. It features significantly in 2-dimensional and 3-dimensional graphics. And one of the key ideas we're going to see there is this notion of a linear transformation between vector spaces. And this is very important in simplifying, in streamlining how complicated graphics effects can be implemented. And that's what we're going to look at in the next slide.